All right, I'm going to give a bit of a rundown of some of the recent Crimson work and a more detailed dive into the ongoing CStore work. So first, a bit of a refresher. So what is Crimson? Um, Crimson is an effort to replace Ceph OSD with a new implementation, Crimson OSD, which is better suited to the demands of next generation storage hardware by requiring less CPU overhead per IOP. So the important thing here that we're trying to improve isn't so much throughput, although that should hopefully be the outcome. It's to improve throughput per core. Classic OSD is capable of driving a great deal of throughput. It's just that it requires a lot of cores to do so. So we'd like to improve that. Um, there are a few ways we're looking at doing this. We're using the CStore framework to try to avoid context switching. Context switching is one of the larger drivers of overhead in classic OSD. And Crimson tries to avoid this by allocating a single thread per core and partitioning all data structures and work among those cores so that accesses tend to be core local, so that locks and cross-core communication can be minimized. Let's talk a bit about what's been happening lately. Recent Crimson work has focused on a few broad areas. Implementing Rados features, data durability and reliability, visibility and debugging, and stability. So because Crimson is essentially a rewrite of the OSD, every feature will eventually need to be ported over one way or another. Recent work has focused on getting RBD workloads up and running for a couple of reasons. One, it's in a way the most sort of straightforward workload. Another is that RBD workloads tend to be the ones most sensitive to CPU overhead in the core write path. So it seemed like a good place to start so we can start getting good performance information. So to that end, we've added better watch notify support, mainly correct support for timeouts, but also lots of bug fixes. In general, better object class API support, mainly OMAP so that we can correctly support RBD header objects. And Joyhan has added better OSD client top pipelining after identifying it as a bottleneck in RBD testing. So as Crimson is a drop-in replacement for Ceph OSD, it also needs to implement all of the relevant data reliability and durability features that we rely on. So recently, Radek managed to merge the backfill implementation last year with some initial testing, and Ronan did some work to refactor Scrub to enable code sharing between the classic OSD implementation and Crimson, and an initial version has been ported to Crimson. So backfill should be the last piece to enable Crimson to do appropriate failure recovery and rebalancing, and should allow Crimson now to survive Toothology failure injection testing. And Scrub gives us a way to ensure that backfill is doing its job, to ensure that the Crimson's I/O and recovery pathways aren't introducing corruption. As Crimson starts to approach a state where a wider audience might be interested in testing and benchmarking it, it's important to improve debugging and performance visibility. So to that end, the team has been working on wiring up something like perf counters using CStore's metric framework and exposing these counters through a Prometheus endpoint for larger cluster level statistics aggregation. Work has also been done to improve backtraces on crash, although more work will need to be done there. The main focus, though, lately and going forward, has been stability. Crimson can now be tested with Toothology and has an initial suite of tests in QA Suite's Crimson Rados. Tons of work has gone into expanding that set and fixing the exposed crashes. This will likely be the major focus for the next release and probably several releases thereafter. So the other major area that's been seeing a lot of effort is CStore. So now that we've gone through some of the stuff that's been going into Crimson, I thought I'd go a bit deeper into CStore so people can get some insight. So CStore is a new object store implementation designed from the ground up for Crimson's threading callback model. It's designed to avoid CPU-heavy metadata designs like RocksDB, and it's intended to exploit emerging storage technologies like ZNS, ZNS persistent memory, and in general, fast NVMe devices. So I mentioned ZNS. ZNS is a new NVMe specification intended to address challenges with conventional FTL-based flash designs. Traditional SSDs implement what is essentially a log-structured file system internally, where writes are performed to free regions of the disk, with a dynamic logical to physical mapping being updated in the background. Doing random writes to one of those regions of the disk first requires relocating the data and erasing it, because you can't do a random write on an SSD. You need to do writes in erasure block sized chunks. The upshot of all of this is that the FTL tends to impose fairly high write amplification and a lot of background garbage collection, which tends to create sort of non-deterministic latency properties. The write amplification is particularly a problem for new quad-level cell flash technologies with relatively low write endurance properties. So where ZNS differs is that it changes the interface to the drive by dividing the drive into zones, which can only be opened, written sequentially, closed, and released. We also sort of hope that this kind of write pattern will tend to be good for conventional SSDs as well, as it tends to reduce the amount of garbage collection that will need to be done and to reduce the amount of write amplification. The other major technology that we want to address here is persistent memory. It has almost DRAM-like read latencies, write latency dramatically lower than flash, and very high write endurance. So it seems like a good fit for persistently caching data and metadata, particularly data and metadata with high update rates that would otherwise have an impact on the write endurance of an underlying QLC device. So the approach that's being discussed, this is a little ways out, hopefully this year, is to keep the caching layer in persistent memory and to maintain a copy on write scatter to extent mapping maintained via the write ahead journal, so that we can rebuild the sort of cache mapping on restart. So that's what CStore is. Let's talk a bit about the high-level design. So the first thing is, what do we actually need from an object store inside of an OSD? So the main characteristics are that it needs to be transactional. It's composed of a flat object namespace. Object names may be large, and they may be under the control of the user in the case of RGW. Each object contains a key-to-value mapping, as well as a data payload. The key-to-value mapping is used for RGW bucket indices and CephFS directories, among other things. We also need to be able to support copy on write object clones for a lot of features, including CephFS snapshots and RBD snapshots. And we need to support ordered listing of both the OMAP and object namespace. So the really, really high-level logical structure of CStore is we have a sort of a root block pointing at an O-node index, mapping H objects to O-nodes, each of which contains a sort of pointer to an OMAP tree for that key-to-value mapping and a set of contiguous logical LBAs for the actual object data. The other half of the metadata structure is this LBA tree, which is how we map logical addresses used on the left side of this diagram to physical on-disk locations. So why do we need an LBA indirection? It's about garbage collection and relocating data. So if we have some internal structure on disk with three extents A, B, and C, with A referencing B referencing C, if these are physical mappings, then if we relocate C to C prime here, we need to update B and transitively, therefore, eventually update A once B gets relocated. Um, this is potentially relatively expensive in terms of write amplification. By contrast, if these references are logical, then all we need to do is update the logical mapping for C. The logical mapping only needs to maintain the sort of basically 64-bit to 64-bit mapping. So it has considerably higher fan out than, for instance, the OMAP or ONode trees. So we should be able to trade extra reads in the lookup path for lower write amplification during garbage collection. It also makes a bunch of other things way easier, including ref counting and subtree sharing for copy on write clones. And it allows us to do sparse mapping for object data extents, which we would otherwise need another data structure to handle. So the OnDisk layout of the journal looks something like this. Each journal unit is called a record, and a record contains a header with all of the usual checksum and length information, a set of deltas, which are sort of mutation records for existing on-disk extents, and a set of new extents, including logical or physical blocks, where logical blocks are data or things at the left side of the tree, really, and physical blocks are really just the blocks comprising the LBA tree itself. So here, new blocks B and A get written, and they're sort of in magenta here, with A being part of the LBA tree. And D prime and E prime are the new representations for the D and D extents after these two deltas are applied. So this structure allows us to atomically mutate existing extents, as well as write new ones. This is important for ZNS because we are able to logically mutate extents without actually mutating them. We don't need to actually rewrite D and D or go back to where they are on disk and rewrite them. We can just write down a record explaining how the extent should be modified. There's another wrinkle, which is that with ZNS devices, we don't necessarily, it might be possible to predict where this record will show up on disk, but it's more efficient if we don't, as it would increase concurrency. So these internal arrows here from E prime to A and from A to B, these are expressed in terms of relative addresses, so that when we read this record back off of disk, there's a step where we need to adjust any of the in-extent addresses relative to their own base addresses. This way, these records work regardless of where they actually end up on disk. So at a high level, the architecture looks something like this. There are two major divisions, the things above and below this transaction manager concept. Transaction manager supplies a transactional interface in terms of a logically addressed set of blocks used by data extents and metadata structures like the GH object to ONode index and OMAP trees. The components under it, which are mostly the logical address tree, deal in terms of physically addressed extents. This gives us a way to build these higher level, more complicated data structures in terms of a more uniform, easy to understand interface. And I'm hoping that it will make implementing things like tiering simpler by creating a sort of a unified interface that won't need to worry about it. So now I'm going to sort of talk through some of the pieces that have been merged so far. So the first is the FL tree, or the ONode manager FL tree implementation. It's a sort of a B tree based structure for mapping GH objects to ONodes. If you look in the source code, a GH object is really, I believe, a 7 tuple with a fixed size prefix, shard, pool, and key, a variable sized middle, the object name and namespace, and a fixed suffix, snapshot and generation. The ordering here matters because the traversal order for this index is used for making scrub and backfill behave uniformly across nodes. So we actually need the listing behavior to be well defined here. To save space, internal nodes drop components that are uniform over the whole node. So if you have a long extent of internal nodes that all map to the same pool, they can omit the shard and pool portions of the key, and so on. Internal nodes can also drop components that differ between adjacent keys, so that if you have a sequence of nodes high in the tree, well above the point at which the sort of name comes into play, they don't need to include a name for their child blocks, which also helps to save space. The work was done mainly by Yingzhen at Intel. So the next bit is the B-tree OMAP manager. This is also a B-tree, essentially a B-tree structure. And it's used for storing the OMAP data for each object. It's a fairly straightforward string-to-string B-tree, contributed mainly by Chunmei at Intel. The object data handler is the component responsible for actually mapping object data to logical extents. It uses the LBA manager to avoid needing to maintain a secondary extent map. Clone work is still, or clone support is still a to-do, and requires the ability to relocate logical extent ranges, which is future work. So this transaction manager is the sort of intermediate layer between everything I've mentioned so far and the lower level implementation details. This is what actually this is the layer responsible for maintaining transactional atomicity, and it's responsible for detecting conflicts between transactions. Users of this interface can create a dependent delta data type, which can be included transparently in the commit journal record. This enables, for instance, the B-tree OMAP manager to represent the insertion of a key into a block by encoding just that key value pair, rather than needing to encode the full new copy of the block or everything after the point in the block where that key shows up. So it allows more compact encodings. Components using Transaction Manager can ignore extent relocation completely. The LBA manager is yet another B-tree, this one mapping logical addresses to physical offsets. It also includes reference counts so that we can use it with clones, and later on it's where we'll put extent checksums. The cache component manages in-memory, a set of in-memory extents, including mainly any dirty extents whose current representation differs from the OnDisk representation due to deltas that have been written between when the extent was written and now. It also is the component responsible for detecting conflicts. Finally, the journal is responsible for actually handling atomic write and replay of journal records. The segment cleaner is the component responsible for garbage collection. It also tracks the sort of usage status of segments. It runs a background process, though within the same reactor thread, that sort of in a loop chooses a segment, relocates any live extents within it, and then releases it. For logical extents are simply remapped within the LBA manager. Physical extents, again, the B-tree LBA manager extents themselves, have a mechanism for finding their parent node and updating the physical pointers. It's also responsible for throttling foreground work based on pending garbage collection work. This is very much a work in progress, but the goal is to avoid abrupt GC pauses and to generally smooth out latency so that we are able to sort of garbage collect as we go. So the status is that we have very initial OSD support just merged in that there's a vstart-CStore command line option that will allow you to start and almost immediately crash an OSD once you do any actual I/O. Though it doesn't support, well, in addition to crashing, it also doesn't support snapshots, other things. The ongoing work will be to stabilize this to the point where, all of the features that exist actually work. And then to start working on optimizing performance, particularly the garbage collection, I think will be an important focus in the near future. And then we need the ability to remap logical extents to support clone. And then slightly further out, we're working on in-place mutation support for fast NVMe devices. What I described here so far is focused on ZNS and slower SSDs where sequential writes are helpful. But for faster devices like Optane, that's not really helpful. So we're working on adapting the internal interfaces to enable direct mutation for devices where that's efficient. And then we're also working on adding support for persistent memory. Somewhat further out, we want to add support for tiering so that we can combine fast small devices with slower, higher capacity devices. For instance, persistent memory with QLC or Optane with, well, also QLC, that kind of thing. I think that's all I've got. Do we have any questions?
There's a question in the pad. Can you explain the role of SPDK? Is it layered above or below CStore?
SPDK, if it comes into play at all, will be below it. So the low-level I/O details need to be plumbed through CStar rather. Sorry. So that's how that would work. It would be an alternative to the POSIX-based accesses we're using so far. Oh, question. Crimson OSD going to support BlueStore initially? It actually does right now. So CStore is a whole different thing. This is a different way of doing storage. Right now, Crimson OSD already supports BlueStore via sort of a queuing separate threads system. So yeah, Crimson OSD will support BlueStore or does support BlueStore. IOPS performance increase of a Crimson OSD SSD with BlueStore? Not directly, no, sorry. Particularly CStore. CStore is really immature. We don't really have data on that. Someone else may have data on Crimson with BlueStore, though. It didn't, so the design of CStore didn't really come from a university research project. It's pretty similar in a lot of ways to Btrfs and other log structured file system implementations, and it's not wildly dissimilar from FFS either. The ZNS wrinkle encourages a design that has log structured file system components, but other than that, it's not really that different from a lot of other approaches that have been done, I think. I think the ZNS thing is something manufacturers are promoting because of demands from the market. It would enable higher capacity, cheaper devices with less on-disk or with less on-device complexity.
There's
Another
one other question.
question. Oh, Sage.
Sorry, yeah, there's one other question in the pad. Is there
Oh,
integration with the NVMe over Fabric gateway?
no. Do you mean for Crimson in general or for CStore? To both questions at the moment, the answer is no. In the future, possibly. Depending on exactly how the NVMe over Fabric gateway ends up evolving, there may be some common work. For instance, in both cases, it may be a good idea to, well, for Crimson, we're definitely going to need to create a version of Liberatos uh, from the objector down that deals with the C-star reactor thread model correctly, and that is likely to be of use to the NVMe over Fabric gateway as well. And there may be future work or future things where NVMe over Fabric may be useful in Crimson. So there may be some overlap there in the future.
Do you have a sense of what milestones do we sort of expect to hit in the Quincy timeframe? Where do you think we're going to
For
be around the end of the year, I guess?
Crimson, I
For
think,
Crimson, yeah.
yeah, the goals would be um, a lot more stability, a lot more of the tests ported over. I think that's the main progress marker. For CStore, it'll look like OSDs don't crash anymore. That'll be good. And like starting to evolve like real performance information to get a sense for which things are really important to attack next. But CStore is actually has work being done on a lot of fronts, so it'll sort of depend on where different people put their focus.
My understanding is that the current Crimson OSD is single core,
Yes, that's true.
basically.
Ah, yeah, I didn't mention
Where
that.
what's the current thinking there?
I think the current thinking is still that stability is the more important component, but I do expect that to be addressed at least partially in the next year. It's going to be a fair amount of work though, so there'll be a fair amount of underlying work to modify the messenger OSD interface and then the OSD backing store interface. At least with BlueStore, it won't be so, the latter bit won't be so complicated since all of the cores are just going to share the same BlueStore instance. For CStore, it'll be more complicated, but CStore isn't quite to that point either. Yep.
Yeah.
I think the main thing is that one of the biggest like danger points of going to multiple cores is messing up the op ordering and correctness details in hopefully fewer of the ways than we managed to in Classic over the years. And having a decent test suite filled out will really help with that. So any stability work we do before that will be really helpful in terms of getting it done quicker.
Cool. Okay. Anybody else have any other questions?
All right. Well, thank you, Sam.